Greetings, mathophiles, and welcome to the third in a series of 3 videos on binomial probabilities. In the first one, we took a look at the formula and the conditions. In the second one, we looked at how to use commands on the TI-84 calculator. And we're going to look now at the shapes of distributions and how they're influenced by the number of trials and the probability of success per trial, and how they're measured in terms of their location and their spread. Here is a Desmos screen that's set up to show us some binomial distributions graphically. The command is an easy one. If you know how to use Desmos, it says binomial dist, comma, the number of trials, comma, the probability of success per trial. So it's an easy command to generate, and it will then make the graph for you. And so I have entered 7 trials and a probability of success of 0.65. And those of you who've seen the first couple of videos know that that comes from a problem that we had involving a free throw shooter. So this is the distribution of probabilities for the numbers of shots from 0 to 7 under that situation. And these are clickable. So if we wanted to know the probability of 3 successes, it's about 0.14 something. If we wanted to know the probability of 6 successes, it's about 0.18 something, and so on. But let's ask ourselves the question, what happens if she still takes 7 free throws in a game, but we presume various levels of skill, various probabilities of hitting a shot? So if her skills are such that she hits 80% of her shots, notice how it bunches up to the right. Notice, in fact, this one is even off the screen, so we'll have to adjust a little bit in order to see it. But notice how when the probability of success on an individual trial is higher, larger numbers of successes are relatively more likely. Should make perfect intuitive sense. If I keep imagining a greater and greater probability of hitting the shot, it's going to bunch still farther to the right. If I imagine that she's not so skilled, a free throw shooter, then we're going to bunch up to the left. Only makes sense. And if we had somebody who was exactly a 50% shooter, we should see a symmetric distribution. If success is exactly as likely as failure, then as we go a given distance from the center of the distribution, corresponding numbers of successes ought to have the same probability as well. And so for p equals 0.5, these things are symmetric. There's also a certain kind of symmetry going on from one side to the other. If we had, say, a 20% free throw shooter, their distribution would look like this. If we had an 80% free throw shooter, their distribution would look like this. And those two distributions are symmetric to one another across the middle of the distribution. So if the two probabilities add to 1, the distribution for a given n, the distributions are symmetric. Only makes sense because if your probability of making a shot is 0.8, your probability of missing is 0.2 and vice versa. So there should be some sort of graphical relationship. I've got a measure also on the screen of the mean and the standard deviation of these distributions. And it should be not a surprise at all that the mean number of shots that one makes out of the 7 is greater, the greater the likelihood of hitting an individual shot, and it's smaller, the less the likelihood of hitting an individual shot. Similarly, if you take a look at the standard deviation, the standard deviation is smaller as we get towards the sides, and it is larger as we get towards 0.5, and then it gets smaller again. This only makes sense as well if you think intuitively, because these probabilities, if you look at the graph, are relatively spread out. These are considerably more bunched to the right. So there should be a lesser measure of their spread. These are bunched to the left. Again, should be a lesser measure. So bigger p's give you bigger means, other things being equal. Smaller p's give you smaller means. P's that are more extreme give you a smaller standard deviation. P's that are towards 0.5 give you a greater standard deviation. If we look at the role of n, there should be no surprises here. As more successes become possible, As the distribution spreads out farther and farther, because it now has a greater domain, we should expect to see the graph sort of morphing to the right in a sense. And we should expect the average height of the bars to be decreasing because the heights have to add to 1 because they're the probabilities in a probability distribution. So if I spread them out over 8 outcomes or I spread them out over 37 outcomes, on average, the values are going to be less across the 37 than across the 8. If you look at the mean, should surprise no one that larger n's give larger means, smaller n's give smaller means for a given p. Standard deviation also is going to increase, if only because we simply have more outcomes across which to spread the probability. There are actually formulas for the mean and for the standard deviation, and they go like this. Just for the record, we'll switch over to the document camera. Here we are on the document camera. The mean of a binomial distribution is it's represented by the Greek letter mu, and it's going to be the number of trials times the probability of success on a trial. This makes perfect sense. If you flip a coin 10 times, you expect to see 5 heads. You may see more, you may see less. You expect to see 5, which is half, or 0.5, times the 10. The standard deviation of a binomial distribution represented with a lowercase sigma is the square root of the number of trials times the probability of success times the probability of failure. And if you play with that p times 1 minus p a little bit, it's easy to convince yourself that that's going to take on its greatest value when p is 0.5. So this has been a quick look at a few features of binomial probability distributions, how those features are affected by the values of n and p, and how to calculate a mean and a standard deviation. Hope it's been engaging. Hope it's been helpful. Happy mathing, everybody.